So here we are in a stellar nebula. These are some of the most beautiful images I see on the internet, and these are just massive clouds of dust and gas. The current ones we see are normally left over from explosions from other stars. So there's a cycle here, and by the end of this lesson, we'll have looped around back to the beginning of this, where the clouds of dust and gas from a previous star become the materials to be the next star. So when a star begins, you basically have a loose cloud of dust and gas that's not very formed, and there's not a lot happening. It's swirling around. But as soon as you get some material clumping together, you get a bit of instability and you get unbalanced forces. And as a few things start to clump together, they attract more, which attracts a little more, which attracts a little more. And slowly you build up a core of materials because of gravity. Now, this isn't exactly a star yet. We usually call it a protostar, meaning it's on its way to becoming a star. And the reason it's not yet is because fusion hasn't happened yet. This protostar builds up material, it adds on more dust and more gas, the pressure increases, so the temperature increases until we reach that temperature where it can ignite and fusion can begin. So they don't start out very hot. As they're accumulating, the temperature is increasing as we go. So they're starting over on the right-hand side of the HR diagram. So this shows three different pathways that three different masses of protostars are going to take as they approach the main sequence. So we're here in the center. You'll remember that little symbol means the sun. So there's the mass of our sun. And that's roughly the pathway it would take along the HR diagram as it approaches the point when it enters the main sequence, aka when hydrogen begins fusing into helium. So once it has ignited and fusion has started, it is a main sequence star, and then it's going to stay there for about 90% of its lifespan until the hydrogen fusing into helium is complete in the core. This depends very much on the mass. Our sun, we think, took about 20 to 30 million years to do this. So this is a long, slow process to build up enough material. We talked a little bit last day when we were thinking about nucleosynthesis, what happens to the star after it moves off the main sequence. So this is when the hydrogen fusing into helium in the core is finished. We remember some of these conditions. There's no more energy release. We had that collapse because of gravity. And as a result, the temperature increased, the pressure increased, which began that next stage in the chain of fusion reactions. That then reintroduced that outwards pressure and the star expanded. So I had little diagrams that had an original one, a collapsed one, and then a much bigger star. So as it expands, the outer layers end up being quite cool. They end up having a very low density by comparison. So these outer layers in this red giant are not, oh, that says reg. The outer layers in these red giant stars, they're very, very loosely held, and that's going to be important in a few minutes. The other piece we talked about last day was the nuclear reactions that happen in stars of different masses. We talked about how with very small stars, and we are classified as small here, fusion in our star will end with carbon, nitrogen, and oxygen. Larger ones, between 4 and 8 times the mass of our star, are going to be in the neighborhood of oxygen, neon, and magnesium. And then if it's more than 8 times the mass of our sun, it will progress all the way to iron. And these are the ones where we end up with the red supergiants, because at every stage of fusion finishing, collapsing, increasing temperature, increasing pressure, until it's hot enough to restart, every time we had that collapse, And we end up with these massive, massive stars that are cool and not very dense. So what happens when we move off the main sequence? There's an absolutely fabulous table on page 347 of your textbooks that outlines this all really nicely and categorizes the information very, very well. So I would strongly recommend that you have your book and follow along with that because it's done quite comprehensively. So the smaller stars, which are now red giants, they're not very dense. The gas is only loosely held. And once fusion is finished for good, the energy released in those final reactions is enough to sort of blow away those outer layers. So you have the core in the center, and then this outer section, which just sort of floats away. One book I once read referred to this as a cosmic burp. And I loved that line, so I always bring it back in. That the star sort of has a little belch, if you would, and sheds away that outer material. And for some reason, that outer material gets referred to as a planetary nebula. Which is a bit of a misleading term because that name suggests that it's the material that a planet would be formed from. The nebula, the stellar nebula, was the first couple of pictures of the dense gas and dust, sorry. So that name suggests that it's something that will become a planet, which isn't true. It was an early theory about where materials to form planets came from, and the name has stuck. So this core left behind, no more fusion is happening in it. So the core in the center, the remnant, it does cool and it collapses. Just like the whole star did when each stage of fusion was over. And eventually it reaches a point where the electrons repel each other and that keeps it from collapsing any further. So it's almost like a bit of stability. It's not going to collapse any further because those electrons want to repel each other. They would like to stay away from each other. And what's left, this core that is remaining, is what a white dwarf is. So those were the stars that were down in this section of the HR diagram. So it's still shining. It is still hot because of the remnant heat left in the materials. It's warmer than its surroundings. So it still looks like it's shining, but there's no more energy being produced because fusion is over. And eventually these stars will totally cool off. There's an idea that maybe as they continue, I'm going to draw my HR diagram a little bigger here. Here's my main sequence. Here's the white dwarf. One theory about them suggests that as they continue to cool off, they'll continue to dim, until they reach that point there. And right now that's a bit theoretical. The universe has not been around long enough to suggest that maybe these black dwarfs exist. There just hasn't been enough time that's passed by because this radiates very, very, very slowly. So once millions and millions and millions more years have gone by, we might be able to tell if this is a real thing, but we're not sure at this point. So there's a limit on here. The textbook talks about the original star having a limit of around 5 solar masses as the upper limit for the stability. Sometimes you also hear this referred to in terms of the core that's left over. So this is a limit on the core that's called the Chandrasekhar limit. Chandrasekhar was an astrophysicist from India, and this was part of their theory of how stellar evolution works. So the remnant core, they estimated would be as much as 1.4 times the mass of the sun. That's after that cosmic burp, the outer layers are all gone. And beyond that limit, that electron repulsion isn't enough to stop the gravitational collapse. So this stellar core further squeezes inwards. The electrons are not enough to hold it from collapsing further because the mass is too much. And what happens here is in this collapse, this is where we get a supernova from. This happens very, very quickly, unlike the cosmic burp. We get a massive collapse and we get a rebound of material outwards in a big explosion. And that is what the supernova is. What we're left with is still a core of material. And because these electrons have been forced inwards, what we end up getting is electrons and protons fusing together. And not in the same sense as nuclear fusion, but in a sense of being squished together until they become something. So it forms something essentially like a neutron, more or less. And so these remnant cores after a supernova are what neutron stars are. Because of the protons and electrons fusing together to form something like a neutron, they have an excess of neutrons. If we were to look at the chemical composition, we would see isotopes that have many, many more neutrons than we would expect. And these neutrons are massively huge and massively massive, not huge. That size and mass designation gets very important here. They are massively massive and massively dense, because they are very small. So on the right here, we have a neutron star, the core remnant after the supernova. It has a mass of 1.5 times the mass of our sun. And notice the radius there is 10 kilometers. So for scale on the left-hand side, we have a map of Manhattan. So this is the island of Manhattan. You can see Central Park in the center here. For scale, if any of you have been to New York. If you haven't, pull this up on Google Maps so you can see a scale of what size of a map that we are looking at here. So these are very, 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 keep saying very small and very, 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 keep saying very dense cores left over. And overall, this is pretty stable. There's some interesting properties that some of them have around spin, so we can get some interesting information from them. But there's a limit on this too, and if you're following along on the page 347 in your book, this is only intermediate mass stars. This is between 10 and 20 solar masses for the original. But if we're beyond that, that is when we get into the territory of a black hole. So this is called the Oppenheimer-Volkoff limit. These are all named after the astrophysicists who came up with the ideas behind them. And the proper statement of that limit is that the core is approximately 3 times the mass of our sun. So the book mentions these in terms of the original masses. We mention them in terms of the remnant core because that's how they were originally defined. So the neutron stars are stable if the core is under around that amount. But if it's more than that, that is when we get into a black hole. So beyond the Oppenheimer-Volkoff limit, if that star is more than 20 solar masses, this further collapses, takes something that's 1.5 times the mass of our sun and the size of New York City, and further collapse that to something even smaller and even denser. And that's where we get a black hole from. And I can't draw a picture of it because we don't totally know what they look like. It is basically infinitely small and infinitely dense. Important thing to note here is that it's not actually a hole. I think a lot of people picture a wormhole like a tunnel when they think black hole, But really what it is that it's an area where it is so small and so dense that its gravitational field strength is basically infinite. And what I mean by that is that it's strong enough that not even light will escape. So how I picture that is if I were to stand on a gym mat, like the ones you use for high jump, it would bend in a little bit in the center if I stand here. And if I put something even more massive on the center of that gym mat, it would end up even more bent. Put a bigger guy holding things there. And eventually, if I put something so massive into this very tiny little area, I would get something so infinitely bent that not even light could get out. And that is what a black hole is. So it's still the remnant of a star. It's just that its gravitational pull is so strong that not even light gets out, so we perceive it as blackness. But there's no hole.